Good morning. This is the first stats video for section 3.2. The other day you read the first about 4 or so pages of the section and did some exercises. This video will cover that material and also the next section after that. So there will be a second short assignment at the end of this video. And then either 1 or 2 more videos to finish out section 3.2. So this section you read about what's called a regression line. And you probably have seen regression lines or best fit lines. You probably saw them even in an algebra class, maybe not to calculate how to find the equation of the line, but maybe you just fit a line to some data and found the equation. So a regression line is just a line that again, best fit line is a good way to think of it. And this notation I need to be comfortable to. It says y hat equals a plus bx. That's how we say that, y hat. That is the predicted value of y. And then a plus bx. Now, of course, in an algebra class, you learned y equals mx plus b. You've done that for years and years and years. M being the slope and b being the y-intercept. Now, most statisticians prefer to go with a plus bx, but those numbers mean what you might think. A is, in fact, the y-intercept, which is the value, the predicted value of x equals 0. And then b is the slope. And just like the slope of a line in Algebra 1, you have to be able to interpret the slope in a statistics problem. So, and these, there they are down there. I kind of already said the bottom one, the y-intercept. A is the y-intercept, which is the predicted value of y when x equals 0. And b is the slope, the amount by which y is predicted to change when x increases by 1 unit. So that you must be able to interpret the slope if you're given the equation of the best fit line, or if you calculate it, which we'll learn how to do today. You need to be able to interpret those numbers. Now, both of those interpretations are great, but they would both need context. So depending on the context, the A would be the amount of whatever if the whatever was 0. So they have to put context in there. We'll see a couple examples before we're done. So again, AX, A plus BX, or AX, BX, AX plus B, you can move the letters around however you want to. The notation that we're going to use is A plus BX. So that's worth getting comfortable with. All right. So let me scroll down here. Those things scroll, they do. Okay. Okay, so here is some data on some truck values, and we're given the equation of the line. Again, before we're done, we'll figure out how to calculate that line. But for the moment, there's the equation of the line. You notice that this even says it with context. Price hat equals 38,257 minus 0.1629 times miles driven. That really is y hat equals 38,257 minus 0.1629x. Like that's what that equation is. So if you were asked to interpret that, you'll notice that this problem asks, it says, identify the slope, y-intercept, and interpret each in context. So let's see if we can do this before I look at the answers. The y-intercept is 38,257. That is the ordered pair right here. That would mean if the car has been driven 0 miles, its predicted price is $38,257. And the slope, which is this negative 0.1629, now that's negative. So again, that's the change in y as x increases by 1. So in this case, as x goes up by 1 mile, for every additional mile you drive, the price goes down by $0.1629. So let's see which is what, like 16 cents, I think? I don't know. Let's see what it says here. The slope, B equals negative 0.1629, tells us that the price of a used Ford F-150 is predicted to go down by $0.1629, which is 16.29 cents for each additional mile that the truck has been driven. And the y-intercept, 38,257, is the predicted price of a Ford that has been driven 0 miles. Okay. All right. So you have to absolutely, if you're given the equation of a best fit line, a regression line, you absolutely will fairly regularly be asked to interpret the slope or interpret the y-intercept. All right. So now let me remind you, we talked about this with correlation in the last section. I really like this paragraph right here, which you should have read already. It says that a small slope means there's no relationship. Remember, if the data goes down like this data, the slope is fairly not steep. So the slope might be negative 0.1, like very small. That does not mean there's no relationship. Like that correlation could be really strong. So it is very tempting, and we said this back in the last section, to think that steeper lines have stronger relationships. Not true. So again, this sentence right here at the bottom, which says you can't say how strong a relationship is by looking at the size of the slope. And actually, my remarks in the way here, but this slope of in the last example we just did, the slope was negative 0.1629. And this says, if we measured the price in cents instead of dollars, the slope would have been 100 times bigger. It would have been negative 16.29. That's a much bigger slope than negative 0.1629. That would not change at all how good a fit that line is. So again, very tempting to fall into the trap of, oh, the data is not very steep, so there must not be a strong relationship. You need to not fall into that trap. Okay, so that's it for that page. All right, next. Okay, so now let's talk about predicting, and you may have done this in a prior math class. You have some data, and you find the equation of the best fit line, the regression line, and we'll get to how to do that. And then you use that line to predict a value for a specific x value. So here is this same data. So there's the equation, price equals 38,257 minus 0.1629 miles driven. So and there's the data, and with the line drawn in. And then now we're going to predict it. This one says this. This one says, if a used Ford 150 has 100,000 miles on it, the question is, what do we predict the price to be? So we can just evaluate that line at that value of X. So you'll notice that we scroll down a little bit here. There we go. You'll notice that there's 100,000. So that point right there on the predicted line is the point 100,000, comma, and then you do the math. There are my lights. Then you just do the math, and you do 38,257 minus 0.1629 times 100,000 turned out to be 21,967. So, which is right about there. So it's a very common, you have some data points. From those data points, you create a best fit line, a regression line. There's a more specific name for that regression line, which we'll see in a minute here. And then you use that line to predict a y value for a given x value. So according to this regression line, if the car had 100,000 miles, or the truck, sorry, you would expect the price to be $21,967. And then notice this is also a relevant sentence here. It says, just right under the graph, it says the accuracy of the predictions depend on how much the data scatter from the line. So the better the line fits, the better the prediction is. Okay. Okay. So then that's a very common thing, using a line to predict something. But what about this? And a very common question. It says, can we predict the price of a Ford F-150 with 300,000 miles? Well, certainly we could do the math. We can take that number of miles, plug it into the equation, which they did right here. They got a price of negative $10,613, which does not make any sense. If I were selling that car, I'm not going to pay somebody $10,000 to take my car. So you have to know that sometimes predicting can cause some troubles. And let me look up here. You'll notice that the data points, be clear what's here, the data points are all between 0 miles and about 140,000 miles. If you plug in an X value outside of where the values that you have, it is very likely that the result will have no meaning. If you're really careful, sometimes it might, but it's really often it doesn't. There's a name for that. which is called extrapolation. And this green box says it perfectly. Extrapolation is the use of a regression line for prediction far outside the interval of values of the variable x that you use to obtain the line. Such predictions are often not accurate. Please be aware, not that you can't do the math, but be aware that it might have no meaning. Okay. And then you notice here, I like this. It says often, even the y-intercept might be extrapolated. It says often using the regression line to make a prediction for x equals 0, that's the y-intercept, is an extrapolation. That's why the y-intercept isn't always statistically meaningful. So it just kind of depends on the data. Okay, so here's an example that we're going to do the whole thing of. We'll just talk through it and look at the example. Again, you should have read through this section. We haven't yet gotten to the new stuff yet. We're getting there. So, take your understanding. Some data were collected on the weight of male white laboratory rats for the first 25 weeks. A scatter plot of weight and time shows a fairly strong positive linear relationship. The linear regression equation, and there's the equation. Again, at the moment, it gives us the equation of the line. Weight hat or y hat equals 100 plus 40x plus 40 times time. What is the slope? Part number one. What is the slope? And explain what it means in context. Well, you've got to know that the slope is 40, and that means that for each week, you'd expect the weight of the rat to increase by 40, grams? So let's see if that's what that says. It should be 40. For each additional week, we predict that a rat will gain 40 grams of weight. That's interpreting the slope in context. Number two, what's the y-intercept? Explain what it means in context. Well, the y-intercept is 100. That means after 0 weeks, the weight of the rat is 100 grams. And that fits in context. That would be when the rat is born, I suppose. Let's see if that's what it says here. The predicted weight for a newborn rat is 100 grams. So that's reasonable. That y-intercept fits kind of in context. Number three, predict the rat's weight after 16 weeks. So you've got to know that just means evaluating that line at that value. So we'll do the math here. So what math you would do there? It would be y hat equals, what is 100 plus 40 times, we're predicting it after 16 weeks. That's what I think that's 740 maybe. I'm doing some math in my head. So apparently we would expect a rat after 16 weeks to weigh 740 grams. Let's see if that's what it says. 740. And then the fourth one says, should you use this line to predict the rat's weight after 2 years? Well, we're talking weeks, and there are 52 weeks in a year. So I can do the math, that's not the issue. But if I in fact do the math, I get y hat equals 100 plus 40 times 104 weeks. Gonna have to get out my calculator to do that math. This is 100 plus 40 times 104, which is 4,260 grams. And I don't know grams very well, but this problem tells me there's that many grams in a pound. If I divide that by 454, that would be a 9-pound rat. That's a big rat. So obviously rats grow as they age, but just like humans, when they get to adult status, they're not going to keep growing in size and weight. So that's just an example of extrapolation and its potential danger. So the answer says, there it is, 4,260 grams. This is equivalent to 9 pounds, about the weight of a large newborn human. This is unreasonable and is the result of extrapolation. So we have to know what the line is. We have to be able to interpret the slope, interpret the y-intercept, and we have to be able to use the line to predict something. We have to be careful of extrapolation. Okay. And I believe that is where what you did so far leaves off. Okay. So one more new concept here, which is this. Residuals and the least squares regression line. So, all right. So this paragraph I like, so I'm going to read it. It says, in most cases, no line will pass exactly through all the points on a scatter plot. Because we use the line to predict y from x, The prediction errors we make are errors in y, the vertical direction from the scatter plot. A good regression line makes the vertical deviations as small as possible. So here is my same data. Here's my truck data and my miles driven and the price, and the line is driven in there. So you have to know that what's called a residual is how far is a given point from the best fit line, from the regression line. And it's a vertical distance. So in this graph, we have the scatter plot points in red, and then they've just drawn vertical lines up or down from each point to the regression line. And you have to know that those deviations are what's called the residuals. And you have to be able to calculate a residual. So here is how you calculate a residual. It says the residual is the difference between an observed value of the response variable and the value predicted. That is, residual equals observed y minus predicted y. Now, that's perfect the way the book I used to teach from, y minus y hat. Now, that's a residual equals y minus y hat. This book calls that observed minus predicted. The phrase that's stuck in my head is actual minus expected, which is really the same thing. But that's just a phrase that's stuck in my head, a residual. Actual minus expected. What's the actual y value minus what's the expected y value? So you have to know that formula. Residual y minus y hat. You want to memorize it as observed minus predicted, that's great. Actual minus expected. You'll hear me say that regularly because that's what's stuck in my head. So let's talk about actual minus expected. Let me go back up here. So the order matters, actual minus expected. So for instance, let's take, actually, let's look at that. I think it looks at an example down here that will make it easier than me just picking one. So let's look at an example. It says, find and interpret the residual for the four that had 70,593 miles and a price of $21,994. Now, the first thing, you'll notice that if I'm going to give you an entire scatter plot, I said find the residual. You have to know that question doesn't make sense. You're finding a residual for one particular ordered pair. Now, you can do it for every ordered pair if you want to, but you've got to know that a residual is, hey, here's one particular ordered pair, find the residual. So this one wants the 70,583 and 21,994. So let's see if we can find that. Let me clear off the drawings here. So 70,000 and 21,994. Let me see if I can find it up here. 70,000 and I think it's right. 70,000 and what was it? 21,994. So there. Oh, so there it is right there. So that's the actual point that this question is asking for residual. Notice it is below the regression line. And if my residual is actual minus expected, my actual y value is lower than my expected. So my residual is going to be a negative number in this case. So you have to know any point below the line will have a negative residual. And then similarly, any point that happens to be above the regression line is going to have a positive residual. Don't just subtract them and assume it's bigger number minus smaller number. So that's the actual y value was the 21,000. Of course, in order to find the residual, we would need the predicted I. So I think that's what they do down here. So it says find and interpret the residual. So the actual y value is 21,994. We need the predicted or the expected. So you have to plug in 7583 into the line, which they did right here. They found the expected was 26,759. And so the residual is actual minus expected, which is 21,994 minus 26,759. which is negative 4765. I want it to make sense that this particular data point has a negative residual because the data point is below the regression line. And then you have to be able to interpret that number. The question says, find and interpret the residual. It always means in context. So this bottom paragraph right here interprets it. It says the actual price of this truck is $47.65, lower than expected based on its mileage. Now you don't have to. Then it says why it might be lower. Don't have to worry about that. It says it might be, other reasons, accident, need a new paint job. You don't need to make up a story behind it, but you have to be able to interpret it. If a residual is a positive number, then the actual price would be $47.65 more than the expected price based on the number of miles. But this one happens to be negative. Okay. So, and now let's talk about like this actual line which we're talking about. It says the line shown in figure 3.9 makes the residuals as small as possible. So think about it. If I go up here, if I were to draw a different line, like a worse line, and then still draw all of my residuals, those residuals would be longer lines. Like I want to fit the line. What line makes those residuals the smallest? And of course, if I were to add up all the residuals, some positive and some negative, I would actually get the one that would make it smallest. They would actually add up to zero because some would be positive, some would be negative. I want to minimize that, but I can't minimize it at zero. So you may recall back when we found standard deviation, we found this, not the sum of the differences, but the sum of the differences squared. So it turns out that's what we're going to do for this. That's what we're trying to minimize, which is what this says down here. It's called the least squares regression line. You need to recognize that name. That is there's other regression lines. We're finding the least squares. So it says the least squares regression line of y and x is the line that makes the sum of the squared residuals as small as possible. So this picture right here, I like what it's doing. It's to be able to interpret it. So you'll notice, can I zoom in here? I bet I can. Oh, I can. Nice. Okay. So over here, here's this one data point. There's residual. They just made a square out of it. They just whatever the length was, made a square out of it. And we could do that for every data point, which is actually what this picture over here does. It took every data point, took the vertical distance from the line, and made a square out of it. The least squares regression line is the line that the sum of all of those squared areas is as small as possible. And in this case, it turns out the sum of the squared residuals is 461,000. These prices are big numbers. It's a big number. But if I drew any other line and I found each residual and squared it and found the sum of that, it would be bigger than that 461,000 number. So yeah, that's what the least squares regression line does. It minimizes the sum of the squared residuals. That phrase is worth knowing. The least squares regression line minimizes, apparently I'm going with purple, minimizes the sum of the squared residuals. I've seen it a multiple choice question on an AP test. They just need to know that that's what the least squares regression line does. Okay, so now we're not going to worry about properties of that right now, but we need to know how to find the equation of it. So this is, and I've got my calculator right here. I would ask you while you're watching this to get out your calculator and be able to match this on your calculator. So we are going to, like this says let's use the Ford. Oh no, actually I have another example. We're going to do this example. Okay. And I'm going to show you how to do it on the calculator. All right. It says it's time to practice using the familiar SEC football data. That data showed up, I think, back in section 3.1. So we've got for the 12 SEC schools, we've got how many points per game they scored, and we've got how many wins they had. And we are trying to find the best fit line, the least squares regression line. Now you'll notice that they give us the answer. It said you should get y hat equals negative 3.7506 plus 0.4372x. Let's get that. So I would like you, with your calculator, to put the data into L1 and L2. So on your calculator, and I did this, like you don't need to stand here or sit here and watch me input data. I went to stat enter, and I in fact have the number of points per game in L1, and I've got the number of wins in L2. And so I want to find the equation of the best fit line. So you're going to go to, and if like you should be taking notes on this because this is new. You want to go to stat, and you want to go over one to calc. So stat and then calc, and then we're going down on my calculus number 8. We're going, and we did this earlier. We're going to go to ln reg a plus bx. Now you'll notice I had you go there back when we were finding the correlation coefficient R. So ln reg a plus bx, and then I'll remind you when it says ln reg a plus bx, you can type in L1, comma L2, but the calculator will default to that. So if you just hit enter, it assumes that your data is in L1 and L2. If it's in a different list, you have to tell it that. So I'm just going to hit enter, and then it gives me lots of information. You'll recall from last section, the bottom number on here, is R. That's my correlation coefficient, 0.9358. That's a fairly strong linear positive relationship. But you'll notice that it says y equals a plus bx, and it gives me a and it gives me b. You have to recognize that a is the y-intercept, negative 3.75, and b is the slope, 0.4372. That line that says r squared, we'll actually get to that in the next video. You can ignore it for the moment. But this screen gives you the slope and y-intercept of that line. And those numbers right there, the y-intercept of negative 3.75 and the slope of 0.437, should in fact match, and they do in fact match. Right there. So you have to be able to find the equation of the best fit line. Now, could we also interpret the slope? Yes. The slope is the slope is negative 0.37506. What does that mean? If a team scored 0 points per game, we would expect them to win negative 3.76 games. That, of course, makes no sense. In this case, the y-intercept is not relevant due to extrapolation that has no statistical meaning. What about the slope? Let's identify and interpret the slope. The slope is 0.4372. That means for each additional 1 point scored per game, the expected number of wins goes up by 0.4372. And I could have asked you to predict the number of wins for a team that scored 22.8 points per game. We could use that line to predict that. We could find a residual. The question could say, find a residual for Florida. Like, they had 25.57 points per game and 7 wins. What's the residual? You would find the actual Y value is 7. You would find the predicted Y value, and you would do actual minus expected to find the residual. So all the things we've done, you could do with that data. And then this is important. So I'm going to read it to you. This book often gives you these AP exam tips. They're always worth reading. It says, when displaying the equation of a least squares regression line, the calculator will report the slope intercept with much more precision than we need. It gave, this on here, there's lots of decimal places. However, there is no firm rule for how many decimal places to show. The AP stats test doesn't say. It says, our advice, decide how much to round based on the context of the problem. I would always err on the side of over rounding. Like, it'd be stupid that, let's see, the slope is 0.437. Don't round that down to 0.4. I would give that a few decimal places. You want to call the y-intercept negative 3.75. So no hard and fast rule, but be aware of what precision the problem might need. Okay. I think that is it, because this stuff, the next thing is for the next video. So that is the end of this video. And your assignment, which again, which should be labeled on the title of the video, is just numbers 45 through 48. Now, if you did not yet do 37 to 42, you should have done those already. Those might now make more sense after this video. You can go back and do those and turn those in again. But then the actual assignment is 45 through 48, which starts on page 193. So that is it, 193. Have a great Tuesday. Turn this off and let me turn